So everybody's so far so good with chapter 4. Okay, so we're going to continue to talk about probability, and today we're going to start with marginal, union, joint, and conditional probabilities. So joint probability makes sense, is the probability that two events will occur simultaneously. Can anybody think of a real life situation where two events occur simultaneously? Anyone? Yep, that's one. What about in nature? Anything in nature that you can think of where two events will occur simultaneously? Okay, maybe I'm thinking this is simultaneous. It doesn't always happen. When it rains, it also may thunder, right? So those are somewhat a simultaneous events. And okay, when it will rain during winter, how is that a simultaneous event, John? John, do you have an answer? Okay, think about it. A marginal probability is a probability of the occurrence of a single event. Okay, so if you look at the table, you see across the top A1, A2 in the total, and then on the sides you have B1, B2 in the total. So the probability of B1, A1 is A over N. Of A2 and B1 is B over N, and the total would be A plus B within brackets divided by N. And then B2 with A1 is C over N. A2 and B2 is D over N, and the total is C plus D divided by N. The total is A plus C divided by N, and for the second total of A2 is B plus D divided by N, and the total is 1, because remember, probabilities always add up to 1. So I'm going to try and get the video for this. So just bear with me. Okay.
Now, when I say basic, I mean probability as it relates to categorical variables, like yes-no type variables. Numerical variables have their own thing going on, and I'll deal with that in later videos. But we're going to be learning through the use of an example here, and here it is. The HBO cable network took a survey of 500 subscribers to determine people's favorite show. Now, in this case, let's say there were two categorical variables, one which is gender, male, female, and the other people's favorite show. So I've got Game of Thrones in there, Westworld, and I've just combined all the others into this other category. I'm thinking that those two are probably the biggest shows on the HBO roster. So let's see how this distribution pans out. Now, out of 500 subscribers, 80 of them are male that like Game of Thrones, 120 of them are female that like Game of Thrones, etc., etc. And each of these squares we can call joint events. They're called joint events because they depend on classes from two different variables. Now, the other thing to note is that, of course, they're all going to add up to this total figure in the bottom right. But we can also calculate this total column and total row, where we just sum up the total number of people that thought Game of Thrones was their favorite show, and that's 200. The total number of people that thought Westworld was their favorite show, and that's 125. And we can also total up the males and females. It's 230 males and 270 females. But this is not quite a probability distribution just yet. So let's see how we get there. Here's the distribution again. And if we divide everything by 500, which is the total number of observations, we get something which is called a probability distribution.
Just a reminder, remember, probability, it has to add up to 1 or 100%. Okay, so that gives you a clue. If you're doing data that looks like this in tables, at the bottom on the right-hand corner, it should always be 1 or 100%.
So where before we had 120 females who preferred Game of Thrones, we now have 0.24 in that cell, because that tells us that 0.24, or 24% of the distribution, is defined by that joint event. So that's why we call that a joint probability. So that 0.24 is called a joint probability. And the way we can write that is to say the probability of female, the event where the person is female, and the event where the person likes Game of Thrones, is 0.24. Now you might see it written with the word and.
Okay, so just so you're aware, you have P of females and Game of Thrones is 24% or 0.24. And that's why it's a joint probability, because you have two variables. One is gender, the other is the television program.
And in between, or else you might see it with this sort of upside down U, which we're going to call intersection. So that's just a fancy statistical term to say the intersection of female and Game of Thrones, which is of course that joint probability. Now collectively, those 6 cells here form what's called the joint probability distribution. So all of these 6 cells are going to add up to 1, because if you think about it, everyone in this distribution has to be in one of these cells. You have to either be male or female, and you have to have selected one of these options. So it's no surprise that this should sum up to 1. Now we can also calculate what's called the marginal probability, called as such because it's in the margins. Another term for this is the simple probability. So just be aware of that if you see the phrase simple probability. But here this 0.4 refers to the raw probability of someone liking Game of Thrones.
Okay, so the marginal probability is when you add up males who like Game of Thrones and females who like Game of Thrones. It gives you a total of 0.4. That's the marginal probability of all your groups liking Game of Thrones. And if you see, when you add up the totals for the marginal probabilities, it should always add up to 1.
I'm sure you can tell it's just the sum of both the male and female joint probabilities. Now, of course, this actual column here is called the marginal probability distribution. So just like we had a joint probability distribution, this one I've highlighted here also sums to 1. Now, the thing to appreciate is that this marginal probability distribution completely ignores gender. It's as if that variable doesn't exist here. But be aware also there's another marginal probability distribution down here. And in this case, it would ignore the show of preference. But again, this is going to sum to 1 because there are 46% males in our sample and 54% females in our sample. And we're going to have to sum them up to get 100%. So our joint probability distribution adds up to 1, but so does both of these marginal probability distributions. Okay, so here's a couple of questions for you. Just using what we've gleaned from the last minute or so, you should be able to answer some of these questions. What's the probability of an HBO subscriber being male? Now,
Okay, anybody? What's the answer to that question? What is the probability of an HBO subscriber being male? 0.46. And how did you get that, Wellington? Add all the males. Right. Okay, thank you.
now, I think I might have even said this before, but the probability of a subscriber being male is purely that marginal probability of the male column, so 0.46. Now, just be aware of terminology. When we say probability, we're after a number that's between 0 and 1. Sometimes they'll ask about percentages and stuff, so you can turn that into a percent. But if it just says probability, you can just leave it as 0.46. Or the next question, what's the probability of an HBO subscriber preferring Westworld? Pretty simple.
Okay. Anybody? 0.2. Where did you get that from? 0.25. Right. Remember, look at the marginal. You have Westworld, your second category here. If we go across, you're ignoring males and females. Basically, you're collapsing that category. You're just taking HBO subscribers preferring Westworld is 0.5.
Well, it's just going to be the 0.25. So you can keep going, appreciating that those first two questions were asking for marginal or simple probabilities. This question asks, what's the probability of an HBO subscriber being male and preferring Westworld? So that's 0.2.
Oh, sorry. Anyway, he went through the answer quickly.
And again, you've got that intersection symbol here. Now here's a slightly different one. It says, what's the probability of an HBO subscriber being male or preferring Westworld?
Okay. Can someone figure out the solution for that? What is the probability of an HBO subscriber being male or preferring Westworld? Oh boy, you got different answers here. 0.2. So remember, the key word is or. Remember in the last video, in the last class, it's either or, okay? Being male or preferring Westworld. So it has to meet both conditions. So what you're saying is, what meets this condition is 0.2.
So this is not an intersection. It's not a joint probability. It actually requires us to think just a little bit and appreciate that to find this, we're going to have to sum up all of the joint probabilities where this condition is met. So if the subscriber is male, we're in this.
Okay, so I want you to pay attention. Remember, it's both conditions because it's or. So just look at this carefully.
Column, so we can highlight these three cells green, and we can also highlight the Westworld row green as well. So in summing up those four cells, we're going to be able to get probability. And you can see here, I've just gone all of those numbers added together, and I've got 0.51. Now you might have noticed I used this upwards U here, and this is the symbol that we call union. So this is the union of two events.
Okay, so if you recall in the last video, the union means it has to be this HBO subscriber and, oh sorry, an HBO subscriber that's male and preferring Westworld. That's how he got the 0.51. Does anybody not understand that? Okay, and remember the symbols. The one that looks like a U is an and. The one that looks like the upside down U or an N is the intersection of the two.
Of someone being male and the event someone liking Westworld. Now, if you've watched a few of my other videos, you might know that I tend not to like formulas too much because formulas tend to stop us thinking, and many of them have an intuitive basis to start with. And this is true of this formula here, which provides us a way of calculating the union between two events. So you might have seen this somewhere where we say union between events A and B is the probability of A plus the probability of B minus the intersection. And again, you can calculate this one that way if you'd like, which is to say that we add up the two marginal probabilities, the 0.25 and the 0.46, and then we subtract the joint probability at 0.2. Now, why do we subtract the 0.2? Well, if you think about each of these joint probabilities, this one here sums up the entire row for Westworld. This one here sums up the entire column for male. Thus, we've actually added this cell twice, the male Westworld joint probability. We've added that twice if we've just simply added these two cells together. So we have to subtract one of those away again to be left with 0.51, which is no surprise the same answer we got using the other method. This brings us to the next and more tricky type of probability, which is called a conditional probability. So here I've given you a question again as an example. Noni just got an HBO subscription. What's the chance that her favorite show will be Game of Thrones?
Okay, so see if you can figure this one out. You know that Noni is female. So what is the probability that her favorite show will be Game of Thrones? 0.24. Okay, 0.24. Anybody say anything other than 0.24? No? All right, let's see.
Now again, you might have seen a formula that looks a little bit like this, where this says the probability of event A given event B equals the intersection of the two events divided by the probability of the condition. So in this case, what we do is we basically focus on the part of this distribution which is of interest. And if Noni is female, we can ignore the rest of the table completely. We're only really considering this column here. We take the joint probability, which is 0.24, and we divide by the probability of the condition, which is 0.54. Now, the condition was that she was female. That was given in the question. So we can calculate this as 0.24 divided by 0.54, which is 0.44444, which is about 4/9.
Okay, I just want to mention something. Does anybody not understand how he got the 0.444? Okay, everybody understands that. I just want to mention something which I have not mentioned, is that when you are providing an answer with decimals, usually it's for 2 decimals, or in this case, if it's a 0.444, which seems repeating, the answer I would like is 0.4 with a bar over it, a line over it, which means that it's repeating. And everybody familiar with that? Anybody not familiar with the bar? Everybody? Okay, good.
But that's okay. We can leave it as a 4 decimal place probability here. So what we could do now is create for ourselves a new column, which is the probability of preferring each of these shows given someone is female. So we just got 0.4444 for Game of Thrones here. Now we can do the same for Westworld and other. We find here what's called the conditional probability distribution. So this is the probability distribution of preferring various shows.
Okay, so if you're going to get a question that has conditional probability, what you have to look at is the actual question. So in this case, it says Noni just got an HBO subscription. Okay, you know that. What is the chance that her favorite show will be Game of Thrones? It's a condition. It is not a fact. So what it's asking you is, what is the probability that her favorite show will be Game of Thrones, having the table that has the preference of shows by gender. So you actually have to figure that out because of that condition. Okay, it's a condition, it's not necessarily a true fact. So remember that.
Given someone is female. And again, because it's a complete probability distribution, it's going to add up to 1, and it does. So what we can do now is we can compare this conditional probability distribution to the marginal probability distribution. That's this one here, the original total distribution. And we can see that if we don't take sex into account, 40% of people like Game of Thrones, 25% like Westworld, 35% like other shows. But when we take gender into account, these change a little bit. So for females, you can see that they're more likely to like Game of Thrones than the general population. They're less likely to like Westworld than the general population. A little bit more likely to like other shows than the general population as well. We can actually use this to assess whether the two variables, gender and show choice, are independent. But before we do, just appreciate that we can also go the other way with our conditions. So for example, if I asked you, given that a subscriber's favorite show is Westworld, what's the probability that they are male? In this case, the condition is that they like Westworld. So our condition is actually an entire row. So much like last time, we can block out the rest of the table that doesn't coincide with Westworld, and we can just focus on this row, and the probability of being male is that 0.2, which is the joint probability, divided by the probability of the condition, 0.25. So if you do that, you get 0.8, and that's the probability of being male if you prefer Westworld. Yeah.
Okay, does everybody, or sorry, let me ask a question the other way. Is there anybody that doesn't understand that? Basically, what you're doing is the condition is it's a male, and the other condition is that it's Westworld. And so what is the probability in that condition? Because 0.25 becomes the actual total. Does anybody not understand that? Okay, good.
In other words, 80% of people that watch Westworld are males. So this leads us to the topic of independence between the variables. Now, we've already touched on it just briefly to show that females have a little bit of a different preference of their HBO shows to the general population. But the strict definition of independence actually has two different approaches. The first of which says that if the two variables are independent, then the probability of A given B is just equal to the probability of A. Another way to think of this is that imposing the condition B doesn't actually affect the probability of A at all. So in our case, we found the probability of liking Westworld if you're female is 0.093. We found that from our conditional probability distribution earlier. But the probability of just preferring Westworld straight up is 0.25. It's in that final value here. It's in that marginal value here. So if these two variables, gender and choice of HBO shows, were independent, these two values should be equal. Therefore, the variables are not independent, as 0.093 does not equal 0.25. So clearly, gender does influence the HBO show that they prefer. Now, it's
okay, I just want to make sure. Does everybody understand that concept? Okay. Why it's not independent? Because one of the conditions, the second condition, is influencing the first. Okay, and therefore there's some kind of dependency, even though it's smaller than, 0.1. So be sure of the logic, depending on what type of question you may get asked. All right.
probably worth mentioning that because this is a sample, you would never expect for these values to be exactly equal, because we know in a sample there's going to be some random variation, and even if the variables were completely independent, these two probabilities wouldn't be perfectly equal. But in this case, I think it's quite clear that they're very different probabilities. One's 25%, one's 9%. So I think we're quite safe to say these variables are not independent. Now, as there's two approaches for assessing independence, and this one says the probability of A union B is equal to the two marginal probabilities multiplied together. Now, I've got a feeling you might understand this equation intuitively. So if I can take you away from this example just for a second, say I flipped a coin in one hand and I rolled a dice in the other hand, and I said, I'm going to give you $100 if I roll a 6 and I flip a head. If both of those events occur, I'll give you $100. And I asked you, what is the probability of me giving you $100? You'd probably say, well, that's 1 in 12, right? You've got half a chance of getting a head, a sixth of a chance of rolling a 6. So you multiply them together. You're going to do the probability of A, getting a head, times the probability of B, and you're going to get that joint probability. But the only reason you can do that is because rolling a dice and flipping a coin are completely independent variables. It's not as if rolling a 6 influences the chance of getting a head, right? So as I said, you can kind of intuitively understand this formula. But what that implies for our distribution here is that if we were to look at the intersection between Westworld and female, we get 0.05. And if you multiply the two marginal values together, the 0.54 and the 0.25, you get 0.14. So again, these two values are not the same, so we can say they're not independent variables, which is no surprise because we just showed this using the other approach. So either of these approaches would be fine to show that people's preference of HBO shows does depend on their gender. All right, so that's a wrap. We've dealt with joint.
Okay. So are there any questions regarding that? If you think about it, it's quite logical. So that's what your approach has to be. You have to be logical. Don't rush through anything. Okay, so, and the last one, conditional, the probability that event A will occur given that, or on the condition that event B has already occurred, is denoted by PA, and whatever you want to call that, straight line given B. Okay, so PA given B is P, the same as AB, probability of A and B, or P of B. Sure, I'm sure why there's 0 there, but it should be times P times B. Okay, that's your conditional probability. All right, we've gone through some of this, but we'll just cover it again just to make sure everybody's got it. So classical and empirical probability. Classical probability, so the probability of an event equals the number of favorable outcomes divided by the total number of possible outcomes. So if you consider an experiment of rolling a 6-sided die, everybody's favorite experiment, what is the probability of the event an even number of spots appear up? So when you roll it, the even ones appear. Okay? So in a 6-sided die, how many even numbers are there? 3, right. Okay, so everybody knows, everybody's played dice, yes, okay. So there are 3 favorable outcomes, 2, 4, and 6, in the collection of 6 equally likely possible outcomes. So 3 out of 6 is, what's the probability? Yep, okay, 50%, 1 and 2, or 3 out of 6, right, okay. And empirical probability is about the empirical approach to probability is based on what is called the law of large numbers. The key to establishing probabilities empirically is that more observations will provide a more accurate estimate of the probability. And this is sort of connected with what we discussed earlier about when you're collecting data. The more data that you have, that you collect, will result in a mean that's closer to the population mean. And it will be more an accurate estimate. So the example, on February 1st, 2003, the space shuttle Columbia exploded. This was the second disaster in 113 space missions for NASA. On the basis of this information, what is the probability that future mission is successfully completed? So you have the probability of a successful flight equals the number of successful flights over the total number of flights. So 101 out of 113 equals 0.98, or 98% probability that the future missions will be successfully completed. Okay, so you're just taking the actual numbers. So I want to show you the videos associated with this.
What I want to do in this video is give you at least a basic overview of probability. Probability, a word that you've probably heard.
Okay, just to let you know, a lot of the videos, there's replication and overlap from previous videos, but they do get to the point that we're trying to look at. So if you want to take a quick nap, be my guest.
A lot of, and you are probably a little bit familiar with it, but hopefully this will give you a little deeper understanding. So let's say that I have a fair coin over here. So when I talk about a fair coin, I mean that it has an equal chance of landing on one side or another. So you can maybe view it as the sides are equal, their weight is the same on either side. It's not, if I flip it in the air, it's not more likely to land on one side or the other. It's equally likely. And so you have one side of this coin, so this would be the heads, I guess. Try to draw George Washington. I'll assume it's a quarter of some kind. And then the other side, of course, is the tails. So that is heads. The other side right over there is tails. And so if I were to ask you, what is the probability? I'm going to flip a coin. I'm going to flip a coin, and I want to know what is the probability of getting heads. And I could write that like this: the probability of getting heads. And you
okay, everybody should get this. What is the probability of getting heads? Amir, everybody. John, it should always be either 0.5 or 50%, not a half. Okay, that's it. Only 3 people know. Okay.
Probably, just based on that question, have a sense of what it is asking. It's asking for some type of way of getting your hands around an event that's fundamentally random. We don't know whether it's heads or tails, but we can start to describe the chances of it being heads or tails. And we'll talk about different ways of describing that. So one way to think about it, and this is the way that probability tends to be introduced in textbooks, is you say, well, look, how many different equally likely possibilities are there? So how many equally likely possibilities? So number of equally, let me write equally likely possibilities, and of the number of equally possibilities, I care about the number that contain my event right here. So the number of possibilities that meet my constraint, that meet my conditions. So in the case of the probability of figuring out heads, what is the number of equally likely possibilities? Well, there's only 2 possibilities. We're assuming that the coin can't land on its corner and just stand straight up. We're assuming that it lands flat. So there's 2 possibilities here, 2 equally likely possibilities. You could either get heads or you could get tails. And what's the number of possibilities that meet my conditions? Well, there's only one, the condition of heads. So it'll be 1 over 2. So one way to think about it is the probability of getting heads is equal to 1 over 2. It's equal to 1/2. If I wanted to write that as a percentage, we know that 1/2 is the same thing as 50%. Now, another way to think about or conceptualize probability that will give you this exact same answer is to say, well, if I were to run the experiment of flipping a coin, so this flip, you view this as an experiment. I know this is the kind of experiment that you're used to, you don't really think an experiment is doing something in chemistry or physics or all the rest, but an experiment is every time you run this random event. So one way to think about probability is if I were to do this experiment, an experiment many, many, many times, if I do it 1,000 times or 1,000,000 times or 1,000,000,000 times or 1,000,000,000,000 times, and the more the better, what percentage of those would give me what I care about? What percentage of those would give me heads? And so another way to think about this 50% probability of getting heads is if I were to run this experiment tons of times, if I were to run this forever and closer or an infinite number of times, what percentage of those would be heads? You would get this 50%. And you can run that simulation. You can flip a coin, and it's actually a fun thing to do. I encourage you to do it. If you take 100 or 200 quarters or pennies, stick them in a big box, shake the box so you're kind of simultaneously flipping all of the coins, and then count how many of those are going to be heads. And you're going to see that the larger number that you are doing, the more likely you're going to get something really close to 50%. There's always some chance, even if you flip the coin 1,000,000 times, there's some super duper small chance that you get all tails. But the more you do, the more likely that that things are going to trend towards 50% of them are going to be heads. Now let's just apply these same ideas. And while we're starting with probability, at least kind of the basic, this is probably an easier thing to conceptualize, but a lot of times this is actually a helpful one too. This idea that if you run the experiment many times, what percentage of those trials are going to give you what you're asking for? In this case, it was heads. Now let's do another very typical example when you first learn probability, and this is the idea of rolling a die. So here's my die right over here. And of course, you have the different sides of the die. So that's the 1, that's the 2, that's the 3. And what I want to do, and we know, of course, that there are, and I'm assuming this is a fair die, and so there are 6 equally likely possibilities. When you roll this, you could get a 1, a 2, a 3, a 4, a 5, or a 6. And they are all equally likely. So if I were to ask you, what is the probability, given that I'm rolling a fair die, so the experiment is rolling this fair die, what is the probability of getting a 1? Well, what are the number of equally likely possibilities? Well, I have 6 equally likely possibilities. And how many of those meet my conditions? Well, only one of them meets my condition, that right there. So there is a 1/6 probability of rolling a 1. What is the probability? What is the probability of rolling a 1 or a 6? Well, once again, there are 6 equally likely possibilities for what I can get, and there are now 2 possibilities that meet my conditions. I could roll a 1, or I could roll a 6. So now there's 2 equally likely there are 2 possibilities that meet my constraints, my conditions. So there is a 1/3 probability of rolling a 1 or a 6. Now, what is the probability? This might seem a little silly to even ask this question, but I'll ask it just clear. What is the probability of rolling a 2 and a 3?
Okay. Anybody? What is the probability of rolling a 2 and a 3 in a one-sided die, or not one-sided, one die, numbered 1 to 6? Okay, how did you get 1/2, John? It should be, yeah, right. It's 2 out of 6. Remember, they're not weighted. Rolling a 2 and a 3 and a 3, remember that's your condition. It's 2 numbers out of 6 possibilities. Okay?
And I'm just talking about one roll of the die. Well, in any roll of the die, I can only get a 2 or a 3. I'm not talking about taking 2 rolls of this die. So in this situation, there's 6 possibilities, but none of these possibilities are 2 and a 3. None of these are 2 and a 3. 2 and a 3 cannot exist on one trial. You cannot get a 2 and a 3 in the same experiment. These getting a 2 and a 3 are mutually exclusive events. They cannot happen at the same time. So the probability of this is actually 0. There's no way to roll this normal die and all of a sudden you get a 2 and a 3. In fact, and I don't want to confuse you with that because it's just it's kind of abstracted and impossible. So let's cross this out right over here. Now, what is the probability? What is the probability of getting an even number? So again, you have 6 equally likely possibilities when I roll that die. And which of these possibilities meet my conditions? The condition of being even. Well, 2 is even, 4 is even, and 6 is even. So 3 of the possibilities meet my conditions, meet my constraints. So this is 1/2. If I roll a die, I have a 1/2 chance of getting an even number.
Okay.
For this video, we are going to look at
Sorry.
how to find.
So your question, is it 0 out of 6 of getting 2 and 3? Yes, because it's only one die. So you can't get two numbers if you're only rolling one die at once. Does that make sense, Roshani? Yep, okay. Okay, so what I just want to, if you haven't looked at this already, what he was showing was an example of classical probability. Okay, it's very, very simple. You roll a die, you know what the parameter is. It can be 1 to 6. You're flipping a coin. It can either be heads or it can be tails. So those are the parameters. So that's classical probability. Can someone see what a problem is, or would understand what a problem might be if you apply classical theory to all probability questions? No one can see a problem. It doesn't work. Okay, why doesn't it always work, Amir? You don't know. Okay. All right. The thing is, for very, very simple conditions, flipping a coin or rolling a die is not the same as, say, I want to invest money in a stock and you apply classical probability to it. It's either going to go up or it's going to go down. So you make an assumption it's 50%, 50% either way, but you don't take in other factors. What happens if you had some gold stock and you may have found some gold and people are buying the gold in anticipation there's going to be lots of gold. However, after 6 months, you find that there's no more gold. That's a factor that you cannot anticipate, right? So it makes it extremely difficult to say, well, it's a 50% chance you're going to find more gold, or a 50% chance you're not going to find more gold. So it doesn't usually work in practical terms when you have many factors affecting the outcome. Is there any questions about that? Okay. So we're going to whoops. I'm going to show the next video.
The experimental probability. This is also known as the empirical probability. So if you're asked to find either one of those, depending upon the text that you are using, some textbooks call it experimental, while others call it empirical probability. In experimental probability, you have to do some sort of experiment in order to calculate this probability. It could be a poll that was done. It could be an event like rolling a die or flipping a coin and recording the results. So regardless of the probability that you are looking for, what the experiment is, we read this formula as the probability of event E. And event E like I said before, it could be many different things. It could be the results of a poll. Maybe you're looking for a specific outcome. You're maybe looking for the people that agree with a new law that's going to be passed, or with a politician. It could be something like rolling a die or flipping a coin. So what you would do is the probability of event E is equal to the frequency of event E. So whatever you are looking for, like let's say, for example, that we were looking for rolling a 5 on a die. Maybe we rolled the die 12 times. We'd expect to see about 2 5s, but sometimes we may get 3 or maybe even 4 5s out of the 12 rolls. So we would record how many times we got a 5, and then we would put it over the total number of times that we completed the experiment. So the shorthand notation is just F, which represents the frequency, divided by N. It's the same thing as the relative frequency that was found in other videos that I have done. So for this one, we have a survey that was conducted in one of my classes. There were a total of 40 students who were polled, and I asked them if their political leanings were liberal or to the left, moderate or kind of in the middle, or if they tended to lean more to the right, or if they were conservative. The results are given in the table below, and we're going to specifically look for the probability that the next person, like if I were to ask another class and what their leanings were, based on this study of the 40 people that were polled, what is the probability that the next person I ask is liberal? Okay, so for this, what we would do is we would use our formula. So we would say the probability, and I'm just going to write in liberal. I could define a random variable to represent the liberal, the response of liberal. Okay, so I would look at this, and I look specifically at the category that I'm looking for. So if I was looking for moderate, I would look at this one. So the total frequency of students that responded that they leaned to the left, or that they tended to be more liberal, was 14. And then we put it over the total number that were sampled. So I would put it over 40. You can always leave a probability as an unreduced fraction. It just tells us that 14 out of 40. This gives us our N, our sample size. So if I leave it like this, we know that we only polled 40 people, so we wouldn't put a whole lot of weight in this being actual or for the larger population.
Oh, sorry. Sorry about that.
Hello, everyone, and welcome
Whoop.
to Chapter 12. Chapter 12 is all about probability. So in this,
I'm sorry. I don't know what happened. Anyways, to get back to what she was discussing, I do not want you to leave an answer as a fraction. I would like it as a percentage. That's all I wanted to say, and I screwed up the video. So sorry about that.
For this video, we are going to
Okay.
look at how to find the experimental probability. This is also known as better than they understand a fraction like 14 out of 40. So we could convert this to a decimal. And if I do 7 divided by 20, I end up with 0.35 or 35%. So we could say that the probability that the next person polled is liberal is 35%. So the probability that the next person polled responds that they are liberal is 35% based on my sample. Again, this is not concrete. This is just based on a sample of people. And since it's a small sample, you wouldn't want to put it to a much, much larger population. Because I was teaching at a community college, I might try to say that the probability of the next person polled at the specific community college that I teach at is 35%. But again, it's one of those things that you have to be careful about overreaching your results to a larger population. We could also, like I said, just as easily find the probability of somebody responding moderate. So if we wanted to find if we were asked for moderate and liberal, we would just do the 19 over 40. Since this cannot reduce, I would leave it like this. And this ends up being 0.475 or 47.5%. And we could do the same thing for conservative. For this one, this was my least response, so this one would have the lowest probability. For this, it ends up being 17.5%. So we could say that based on the findings from my classes, students tend to be less conservative and they seem to be the most moderate. But again, this was just findings from my, so I would not take and put this to a larger population of saying all people. I would say like the next person polled at my school would be 35%. As always, thanks for watching.
So this introduction.
Okay, sorry, I'm going to go back to the slides. So does everybody understand that is an example of experimental probability? You're actually applying what you want to find out with regards to probability. Or empirical probability. My error, sorry. Okay, now subjective probability. It's the likelihood or probability of a particular event happening that is assigned by an individual based on whatever information is available. If there is little or no past experience or information on which to base a probability, it may be arrived at subjectively. So some illustrations. Estimating the likelihood of the New England Patriots will play in the Super Bowl next year. Estimating the likelihood you will be married before the age of 30. Estimating the likelihood the U.S. budget deficit will be reduced by half in the next 10 years. Okay, this is based, subjective probability is based on your understanding, your experience, your knowledge of a particular area. Okay? Can someone tell me what is the problem with subjective probability? There's no problems with subjective probability? It's based on the past? What past? Amir, you have to be more specific. It's statistics. It's subject. What does subjective mean? Who does not understand the word subjective? Okay, subjective is your own personal belief in whatever is being asked. It is based on your knowledge. It is based on your experience. So what is the problem with that? Bias? It's not the public info? Okay, Brenda, what do you mean by bias? It's personal. Exactly. And as Amir pointed out, it's not public information. We don't know whether it is or it isn't. Yeah, Bertha, that's it. It's a point of view. It's a point of view based on your understanding of whatever the topic is going to be. If you have very little, the probability might be, oh, I say it's 2%. If you have an enormous amount of information, you might go, oh, it's around 10 to 15%, which might be more accurate. Okay? What's the problem with somebody arriving at subjective probability? They give a number out. What do you say about that number? Is it valid? Is it verifiable? Yes, it can be honest, Amir. It doesn't necessarily honest. It's inaccurate, exactly. Okay, the word is inaccurate. It's not that it's dishonest. It's what the person knows personally about any particular discipline, area, topic, subject. Okay? So it's very dangerous if somebody's going to give you subjective probability. Okay? Because unless they are a content expert in that particular area, it's very difficult to believe them. So, look at the video on subjective probability.
The probability will cover subjective probability first, and we're going to take a look at a series of statements and decide on the probability of each. So first, a flipped coin will show tails. It's 50-50 chance, so that we're going to put that as maybe. And next one, I will be in school tomorrow. Yeah, well, if it's Saturday, that's going to be unlikely or improbable, or Friday, it's going to be unlikely or probable. So today's Thursday, so I'm going to say it's likely or probable. And it will not get dark tonight, unless you're in the Yukon in June, then that's going to be empty. I will have vegetables with dinner tonight. That's likely or probable. I will roll a 3 using a die. Oh, that's maybe. And it will snow in July in my hometown. Unlikely or improbable. I will draw an ace from a deck of cards. Well, that's maybe, but I wouldn't say unlikely or improbable because you've got a 1 in 13 chance of doing that. Now, these are all examples of subjective probability, and the definition of subjective probability is that it is an estimate of the likelihood of an event based on intuition or experience. In other words, you're making a guess using statistical data that you have observed in the past. For example, if you consider the following questions. So, for example, you will earn an A in the course. You will pass the course. It will snow tomorrow. You will hear your favorite song on the radio within the next week. All of those the answers to those are based on your past experience and your intuition. So these are all examples of a subjective probability.
Okay. Are there any questions about subjective probability? If you want to think about it another way, when you're having a discussion with your friends, your parents, or somebody else, does the discussion usually come up to personal opinion, or are you or the other person giving facts? Just when you're having a general discussion. Anybody? It's personal. It depends on the discussion. When are you giving them facts, Wellington? What's the example? What's the condition under which you are providing facts in a discussion? Political? And you have data when you're discussing this? Sometimes you do. Okay, good for you. You carry around the data. But the point I'm trying to make here is a lot of this has to do with an opinion that you as an individual has formed based on some kind of information you've received. You don't know the accuracy of the information, and therefore it may be invalid information, but that is how you determine your subjective probability of a question or discussion. So are there any questions about that? Okay. Not for you. Okay, great. All right. So if we look at the summary, how do we know what? What is it what you want to know? How do you distinguish? What are you trying to distinguish? Between fact and opinion? Amir? Ah, your source. So this goes back to the case study that people are going to do. It's where you get your information from. Is it a reliable source? Is it somebody's opinion you talk to on the street, or your friend, or your mother, or your sister, or brother, or whatever? Where is this data coming from? And the validity of the data. Okay? If for example, say you're working at a company and you use the elevator and you work on the 30th floor, and for whatever reason you got nothing better to do, you sort of keep track of how long does it take to go from the first floor to the 30th floor. You go, oh, it takes like 3.5 minutes. The more times you're going to go on that elevator, the closer you're going to get to an actual number. Okay? That's one thing. That can be real data, but you have to check the source of the data. Okay? Somebody's opinion may not be valid data, so you have to go to reliable sources to collect that real data. All right? So this slide is basically just a summary of the types of probability that we've talked about. You have objective, which includes classical, empirical, based on equally likely outcomes, based on relative frequencies, and subjective probability based on available information. So of course, there's mathematical rules in probability. So the first one is the rule of addition in probability. So the special rule of addition says, if two events A and B are mutually exclusive, the probability of one or the other of occurring equals the sum of their probabilities. So the probability of A or B equals the probability of A plus the probability of B. But remember, they must be mutually exclusive. One cannot be dependent on the other. And the general rule of addition is if A and B are two events that are not mutually exclusive, then the probability of A or B is given by the following formula. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Okay, so look at this as A or B, and this is A and B. Okay, this is A or B, and this is A and B. Okay, so an example, an automatic Shaw machine, which I have no idea what it is, fills plastic bags with a mixture of beans, broccoli, and other vegetables. Most of the bags contain the correct weight, but because of the variation in the size of the beans and other vegetables, a package might be underweight or overweight. A check of 4,000 packages filled in the past month revealed the following. Event A, the package is underweight, so the number of packages was 100, okay, out of a total of 4,000. That gave the probability of 0.025. That's 2.5%. They were satisfactory, which was 3,600 out of 4,000, or 90% that this would occur. And if it was overweight, you had 300 out of 4,000, which is 0.075. Add them up, you end up at 1. And this one out of the total is 100 out of 4,000, you get 0.25. So what is the probability that a particular package will be either underweight or overweight? So the formula is the probability of A or C, look at the table, equals the probability of A plus the probability of C, which equals 0.025 plus 0.075 equals 0.1 or 10%. Is there any questions about that example? Okay. So I'm going to look at the video for addition.
The addition
And sorry.
rule using mutually and non-mutually exclusive events. For example, in a deck of cards, there are 52 cards.
Sorry, what were you saying, Amir? 100 over 4 plus 300 over 4 was 4,000, not 4. Yeah. Okay.
Question number 1 asks, what is the probability of selecting a king or queen from a deck of cards? And question number 2 asks, what is the probability of selecting a king or a club from a deck of cards? Question number 1 asks, what is the probability of selecting a king or a queen from a deck of cards? Since we are trying to find the probability of A or B, we are going to use the addition rule. Recall there are 2 formulas for the addition rule. So for the probability of A or B, we can have the probability of A plus the probability of B. And this rule is used for mutually exclusive events. Recall that 2 events are considered mutually exclusive if they do not have any simple events in common. The second formula we are going to use, which again is the probability of A or B, but this time it's equal to the probability of A plus the probability of B minus the probability of A and B. And this formula is used for non-mutually exclusive events. So for our first example, we are going to use the first formula because there are not any cards in common between a king and a queen in a deck of cards. So for example 1, we'll ultimately have the probability of A or B is equal to the probability of A, which is 4 out of 52, plus the probability of B, which is 4 out of 52. Again, you have 4 kings and 4 queens in the deck of cards. Thus, we have 8 out of 52, and that reduces to 2 over 13. The second question asks, what is the probability of selecting a king or a club from a deck of cards? Once again, we are trying to find the probability of A or B. For this example, the events are not mutually exclusive because both share a king of clubs. And therefore, we are going to use the second formula for non-mutually exclusive events. And so to find the probability of A or B using the second formula, again, we find the probability of A, which is 4 out of 52, plus the probability of B, which is 13 out of 52, because we have 30 clubs in a deck, minus the overlap of 1 out of 52. And recall that we're subtracting out the overlap because in probability, things cannot be counted twice. The king of clubs was computed in the first probability, and it was also computed in the second probability. So by subtracting out the overlap, we're able to only count the king of clubs once. So 1 out of 52 is the card that they have in common. Once we simplify, we obtain 16 out of 52, and that reduces to 4 over 13.
Any questions about that example? No? Okay, that's pretty straightforward. Okay. So this is about probability matrices, which you see the table below. This is what's referred to, if you haven't discussed this previously in other classes, this is what's referred to as a matrix. It's a rectangular array of numbers arranged into columns and rows, much like a spreadsheet. The matrix algebra is used in statistics to express collections of data. So for example, in column A, you have the student's name. Column B, their grade on exam 1. In column C, exam 2, and column D, exam 3. Okay, I have a video that talks about probability matrices. It's not something you have to study a lot, but you should be aware of what it is. Okay, this is a 21-minute video. We're not going to do 21 minutes. We're just going to look at some of the examples and the description. Well, you certainly can look at it on your time if you want.
Morning, ladies and gentlemen. It's Professor Williams again, and this time we are going to do some probability featuring the matrix. A probability matrix is simply a grid that we create that we fill with the probabilities of all combinations of events to allow you to solve virtually any question you could be asked about that series of events and their outcomes. So let's get rolling. I worked this same problem earlier using quote unquote formulas, but now what I want to do is I'm going to work it using a probability matrix. The number one rule for a probability matrix is you need 3 pieces of information. I need 2 outside boxes, which are my OR probabilities, and I need 1 inside box. The inside box either needs to be given to me or I need to be given enough information to be able to calculate the value that goes into it. So let's go through real quick, and I'm just going to identify what I've been given. I've been given the fact that 43% of Americans expect to save money next year. I'm also given the information that 45% plan to reduce debt. The key is that what I am also given is that of those who expect to save more money next year, not everyone, just the ones who expect to save. That's our 43%, isn't it? Of this 43%, 81% plan to reduce debt. Well, that means they plan to save and reduce, which is a both box, which is an interior box, And so even though I wasn't given yes, yes, I was given the ability to calculate it. So what is the probability that they're going to save money? 43% given. What's the probability that they're going to reduce debt next year? 45% given. What's the probability that they're going to do both? Not given, but easy to calculate, because it says of those who expect to save more money next year. So of the 43%, 81% of those plan to reduce debt. So what I know is it's 81% of the 43% means I multiply, which gives me 0.3483. Remember, what I know about my matrix is that I need two outsides and an inside. Outside, outside, and this is save yes, reduce yes, which means this is my yes, yes, or both box. So let me go grab a matrix and I'll be right back. All right. What I have done is I've simply set up my probability matrix. The one thing I want to do is I want to make sure that my yes, yes is always right here. Right? I have one characteristic and the other plotted on the two sides. And I also know that all probabilities must equal 1, which means these two have to add up to 1. These two have to add up to 1, and everything inside of here has to add up to 1. So let me take a look and see what this looks like. So go back to our problem, and it says, what is the probability that they save? 43%. There's save. There's yes. Because it doesn't have anything with it, because it's just by itself, it goes right here. Same thing with reduce. Here's reduce. Here's yes. So I know that my yes reducers are going to go right down here because it doesn't have anything with it, does it? And the only thing that goes inside of the matrix, actually inside of the box, are ones that have some of this and some of this. So we can always think of the outside as an or, and we can always think of the outside as an and. All right? So what is the probability that they save? We already said it was 0.43. I also told you that this box and this box have to equal 1. So 1 minus 0.43 will give me my value here. And I know that 1 minus 0.43 is equal to 0.54. So this side is done. Now let's look at our reducers.
5-7.
Reduce, yes.
She can't add.
45%. We said the reduce yes came down here. So now what I'm going to do is I'm going to put right here, I'm going to put my 0.45. I know that if nothing else, this box plus this box has to equal 1. So 1 minus 0.45 is going to give me my value here, which is 0.55. So now my whole outside is filled in. And remember, the insides are all ands, and all I need is one of them. And I calculated this one right here. So this is save yes, reduce yes. Here's yes. Here's yes. Where those two intersect is what we refer to as the yes, yes box. And so all I need to do is drop this 0.3483 into that box right there, and then I can calculate everything else. So here I'm going to put my 0.3483. Oops, got to make my box big. There we go. That looks better. The other thing that you know is that this plus this has to equal this. So now what I have is I have 0.43, this number here, so I subtract this from this, and it gives me this box right here. What else do I know? I know that this plus this has to equal this. So I take 0.45 minus that 0.3483, and now I will have filled in this box, and this box. What else do I know? I know that this plus this has to equal this. So I've just filled in this one. I'm going to subtract this box from this number. It's going to give me this one right here. So let me show you the math. All right, so I filled in my numbers, and in case...
Okay, I'm going to stop it there. Now, does anybody have a question on how, except for the mathematical error, she got this matrix? So how do they did it in Excel? Well, don't worry about that, because I don't know whether she did it in Excel or she didn't do it in Excel. Okay, any questions about how she did this? It seems complicated, but not really. Okay, John, you can email me after. So she knew this, which was a total over here, 0.43. The probability of reducing was 0.045. We know on the margins, these are called margins, this has to add up to 1, both sides. So this should be 0.57, and this is 0.55. So we know what the margin totals are, right? Because they're always add up to 1. She knew what the probability of saving and reducing was equivalent to 0.3483. She figured that out. That was just the addition rule, and put it in here because it was under that condition. Yes, you reduce, and yes, you save, and you get this. She has this filled in for a total of 1. You know this one, so you know that you have to add something to get here. So you subtract the 0.3483 from 0.45. And here you're subtracting 0.3483 from 0.43 and get this. And then you can fill in the other one. So I just want to understand, I want you to understand it's not that complicated. So is everyone good with creating a probability matrix? Is there anybody not sure about that? Or is everybody good? You don't understand, John? What is it you don't understand? Well, you have to have the information, Amir. You're given the marginal totals. The probability of saving, that's the total here, 0.43. The probability of reducing, that's 0.45. John, the total has to be 1. Okay? You're given 0.43, 0.45. If you subtract 0.45 from 1, you get 0.55. If you subtract 0.43 from 0.43 from 1, you get 0.57. She made a mathematical error. No. Listen, John. You figured this one out previously. Remember how she got this number. Okay? This condition is yes, you're saving, and yes, you're reducing. So it goes in here. If you know what's on the margins, you're just subtracting this number from this number to get this cell. You're subtracting this number from this number to get this cell. okay? And then the cells that you know, you're just subtracting because it has to add up to these marginal totals. All right? Okay, any other questions about probability matrices? It's relatively easy. Okay.
Let's talk about probabilities, where they have to do with complementary. If we want to find the probability.
Sorry. Okay. The next rule of probability, the complementary rule, which we discussed earlier last week, was in a video. I'll just go over it. The complement rule is used to determine the probability of an event occurring by subtracting the probability of an event not occurring from 1. So the probability of A plus the probability of not A is equal to 1. Or the probability of A equals 1 minus the probability of not A. Okay? Oh, this is the example we used. But an automatic shaw machine fills the plastic bags with mix of beans, broccoli, and other vegetables. Okay, we figured out this table already, right? So the probability of B, which is satisfactory, equals 1 minus the probability of not B, which equals 1 minus the probability of A or C. Remember, there are 3 events here. It's not B, so it has to be C, equals 1 minus the probability of A plus probability of C equals 1. So 0.025 plus 0.075 equals 1 minus 0.10 equals 0.9. Okay, that's the complementary, because that's all that's left. There's only 3 events. We added 1 and 3 to get the probability of 0.10. We subtracted the total, which remember is always 1. 1 minus 0.1 equals 0.9. Okay? Let's just look at the video.
Of guessing if with complementary events. So the complement of an event A, which in this book is denoted by A with a line over the top, consists of all outcomes in which the event A does not occur. So the complement of A includes all the outcomes in the sample space that are not outcomes in the event A. That means A and A complement together make up the whole sample space. Here we have a picture. This is the whole sample space inside of this box. This in the circle is the event A. So everything outside of the circle is the complement of A. So if we put those 2 together, A and A complement, they give us the whole sample space. An example of complementary events is that a typical question on an SAT test requires the test taker to select one of 5 possible choices, A, B, D, or E. Because only one answer is correct, if you make a random guess, your probability of guessing correctly is 1/5 or 0.2. If we want to find the probability of guessing incorrectly is the complement of the event of guessing correctly. So incorrect is the complement of correct. Now, exactly one of the 5 choices is correct. That means that 4 of the choices are incorrect. So the probability of guessing incorrectly is 4 over 5, because we had 4 incorrect choices out of the 5 total.
Correct.
That means the probability of guessing incorrectly is 4/5, or if as a percentage, it would be 80%. So if we're talking about probabilities for complementary events, we need to think about the relationship between A and its complement. A and A complement are disjoint. That means they don't have anything in common. So it's impossible for an event and its complement to occur at the same time. That gives us a rule to figure out the probability for complementary events. If A and A complement are disjoint, and if together they make up the whole sample space, then the two probabilities added together should equal 1, because we've got 100% of the outcomes in the sample space if we put the two events together. So our first rule is that the probability of A plus the probability of A complement is equal to 1. From that, we can get two other rules, and this is usually how we use this rule. So if we're trying to find the probability of A complement, we can find the probability of A, just subtract it from 1. Or if we're trying to find the probability of the event A, we can find the probability of its complement and subtract that from 1. So this rule works either one of those two ways. Let's look at an example of this. Many individuals age 65 and older rely heavily on prescription drugs. For this group, 82% take prescription drugs regularly. This is according to Money Magazine in September 2001. What's the probability that a randomly selected individual age 65 or older does not take prescription drugs regularly? So if A is the event that a randomly selected individual over 65 does take prescription drugs regularly, then A complement is the event that the individual does not take prescription drugs regularly.
Okay.
Now, we were told in the information up here that 82% of this group does take these drugs regularly. So that means the probability of event A, which would mean a randomly selected individual does take drugs regularly, would be 82%. If we want to find the probability of the complement, all we have to do is take this value and subtract it from 1. So the probability of A complement would be the probability that the randomly selected individual does not take prescription drugs regularly. That would be 1 minus 0.82, and that would be 0.18 or 18%.
Correct, Amir.
Here's another example. If we consider the procedure of rolling a die, let event A consist of rolling a 5, find the probability of event A and its complement, and then we're going to let event B consist of rolling a 2 or less, and we're going to find the probability of event B and its complement. So for part A of this, the event A includes just one outcome, and that is that we roll a 5. The complement of A is the event of not rolling a 5. Since our sample space is all 6 faces on the die, that means A.
So this is the important thing about the complement. In this example, you roll a 5. You figure out what is the probability of rolling a 5, 1 over 6. But the complement of not rolling a 5 is rolling all the other numbers, not, a 2, a 4, whatever. Okay, so remember that. That's very important because you have to look at your sample space. And remember, your sample space consists in here of 6 outcomes. You've already taken one outcome away. That's rolling a 5. So you have to consider all the other possible outcomes. That it becomes the complement in this case for rolling a 5.
A complement is every face except for the 5. So it's 1, 2, 3, 4, and 6. The probability of A, since there was only one outcome in event A, is 1/6. And the probability of a complement is 5/6. So we could get this by either noticing how many events were in our A complement, which is 5, or we could just simply take the probability for A and subtract that from 1. Either way, we would get 5/6. Now for part B in this question, the event B consists of rolling a 2 or less. that includes two outcomes because that could either be rolling a 1 or rolling a 2. So B complement would be every other face on the die that's not already included in this set, which would be 3, 4, 5, and 6. The probability of B, since there were two simple events in this event, would be 2 or 6, which would simplify to 1/3. The probability of B complement would be 1 minus this. So 1 minus 1/3 would equal 2/3. We could also get that answer by looking at how many simple events are in B complement. There are 4 out of the 6 in the sample space. 4/6 would simplify to 2/3. One more example. This is from the table that comes from the survey. And here we want to find the probability of selecting someone who is not over 65 from the 1,000 survey respondents. So one of the keys to figuring out that you can use a complement is this word not. Not always means that the complement of the same event without the not. So if event A is selecting someone who is over 65, then selecting someone not over 65 would be the complement of A. We can find the probability of A by just taking the number of respondents over 65 and dividing by the total number of respondents. So we already have a total for our number that are over 65. That's given to us in the table. That's 315. Our total number of respondents was 1,000. So the probability of A is 0.315. We can use the complement rule to find the probability of A complement by taking this answer and subtracting it from 1. So the probability of A complement is 1 minus 315 over 1,000, or 685 over 1,000, or we could have just taken 1 minus 0.315, and that would give us 0.685.
Okay. Are there any questions about the complementary rule? No, everybody's got this. Good. Well, you want to calculate the space, yes, but the space is very important because it becomes involved in you're figuring out the other probabilities, right? Okay. All right, special law of addition in probability. We looked at the addition rule. When two events A and B are mutually exclusive, the probability that A or B will occur is the sum of the probability of each event. So we have the probability of A or B equals the probability of A plus the probability of B. Your example, a single 6-sided die is rolled, and what is the probability of rolling a 2 or a 5? So the probability of 2 is 1/6. The probability of a 5 is 1/6. So the probability of a 2 or a 5 equals the probability of 2 plus the probability of 5, which is 1/6 plus 1/6 equals 2/6 or 1/3 or 33.33%. All right. So let me just go back here. I won't watch this whole video, but
of how probability rules work. When we say probability, if you look at this notation, you'll see that I've got the probability of an event, we'll call it event E, is equal to 0.25. And I've got another probability, or another event rather, called F, whose probability of F is 0.45. So let's go off and try to find things. And this is coming from a section in our book that has to do with probabilities, and especially something called the addition rule. So maybe I should throw that up here first. The first thing we should know and that you should remember is something called the general addition rule. And what's applicable here, right, is we call it the addition rule because we're going to use addition anytime you see that word or, right? That's when you know that you're going to be using addition as opposed to there's something also called the general multiplication rule.
So remember that. If you see a question with the probability of A or B, you know you're going to use the addition rule.
But anytime it's addition going on, we're going to use the word or. And what's really happening here is, maybe I should draw a little Venn diagram picture. Okay, this is we call it Venn diagram. And I hope you see that, look, I have two events, event E and event F, that overlap a little bit, right? And in this case, this little section right here, where they both overlap, is what's considered my AND. It's considered the probability of E and F. So this portion of the addition rule is the overlap. I hope you see, okay? That's where these two intersect each other. So the addition rule, basically, the general addition rule basically says, find the probability of E, add that to the probability of F, and take away the probability of E and F. That's where they overlap with each other, okay? So now that we know the addition rule, let's go off and try to find this first example here. Let's find the probability of E or F if we know that the probability, right, if we know that the probability of E and F is equal to 0.15. So using that general addition rule that we just saw a second ago, it says, hey, the answer to this, right, so the answer to this probability of E or F is equal to the probability of E added to the probability of F minus the probability of E and F. And we know this. We know the probability of E. They gave us that at the very beginning of the problem, right? So this thing right here is 0.25. We know the probability of F. They gave us that at the very beginning of the problem, which is 0.45. And we're going to take away this AND where they overlap. And we know that too. They overlap with a probability of 0.15. So this problem is really just a simple, hey, let's work this out on our calculator. And I hope you see that it comes out to be minus 0.15. I'm just doing this here on my calculator, and an answer of 0.55, right? 0.55. So there's the answer to that question. Now, what's interesting is we could change this question around a little bit, right? We could change it around a little bit. If this time we say, hey, can we find the probability of E and F? Right? What if we ask it this way? Let's find the probability of E and F if we are told that the probability of E or F is equal to 0.6. Well, it's the same formula, right? It's the same general addition formula, which again looks like this. Probability of E added to the probability of F, take away the probability of where they intersect. And I hope you see that this time, this is what we're looking for, right? This is what we're looking for if we know all of these other things over here. They told us the probability of E or F is 0.6. That's this thing. It's almost like saying, hey, here's the answer to all of this stuff. And we'll use the same probabilities of E and F as we used before, which was 0.25 and 0.45. But this time, we don't know what this is. All right, maybe I'll call it, how about we call it X for now, right? Since I don't know what it is, I'll just call it X. So if I was to just switch over to algebra.
That's what I wanted to mention, is that if you notice, it's just like doing an algebra problem, okay? You have one unknown, the X. Everything else is known. So you're just going to move these numbers over to the left-hand side. So you have a number equals an unknown. That's what your number is going to be. Okay, so if you think in that way, it's probably a lot easier if you're okay with
for a second and ask you, right, if we were to try to find out what x is, the algebra here, I hope you see, is how about we add x to both sides? In other words, let's bring this term over to the other side. I'm going to move this over here to this side, becomes a positive x. And I'm going to take away 0.6 from both sides and kind of move it over here. Right? So now on the right-hand side, I have 0.25 plus 0.45 minus 0.6. And now if I work all this out, I'll get the value of x. And that value of x is the probability of E and F. All right, so working this out here on my calculator. Let's see if this works out here. I've got 0.25, added a 0.45, and we're going to take away 0.6. Let's see if we can slide that over so you can see that. And that comes out to be 0.1. So there's my total answer for this one. Where they intersect in this case is 10%, right, or 0.1. So I hope that helps. Maybe I should show just maybe one more of these examples of how things are mutually exclusive or not mutually exclusive. Here, take a look at this one now. How about using the same numbers here, right? How about using the same numbers? We ask, find the probability of E or F if E and F are mutually exclusive. All right. Another word for mutually exclusive, by the way, another word for that is that they are disjoint. Perhaps your book uses that as well. All right, disjoint, another word for mutually exclusive. Well, if they're disjoint, then this is the picture going on here. Right? The Venn diagram would look like this. Here's E, and here's F, and they don't cross each other at all. They don't intersect, and it's a terrible looking circle there for F, but look, they have no intersection whatsoever. So this is going to be pretty simple. You simply take the probability of E, which in our case was 0.25, and you add it to the probability of F, which in our case was 0.45. Right? Using the general addition rule, we're just going to add those two numbers up. Right? So you want to find E or F, it's simply just add these two numbers up. Minus where they overlap. Right? Where they overlap. But did they overlap anywhere in this picture if they're mutually exclusive or disjoint? No, they don't overlap at all. Therefore, it's really just the sum of these two probabilities. You can think of it as -0 if you want for where they overlap, but you don't even have to do that. So they're mutually exclusive. If they are disjoint, it's a simple matter of just adding up 0.25 to 0.45 and getting an answer of 0.7. There it is. So if they are mutually exclusive, there's our correct answer of 0.7. Hope that helps.
Okay. So you can see that you can convert these questions into an algebraic question where you have one unknown and you have all the other variables known, and just solve that way if you're comfortable with that. So what I'm going to do is we're going to stop here. I just have a couple of administrative things to mention. One, I believe I said it in the announcements, your homework is due on Tuesday for Chapter 4. We will continue with Chapter 4 and probably complete Chapter 4 on Tuesday, which means the test will become available next Friday at 5 p.m. and goes till Monday at 5 p.m. So is there any questions that people have? I hope that the videos and the explanations are helping you understand that probability isn't that complicated. It's more about you understanding the logic that's involved in the presentation. Yes, I received your homework, John. So, any questions? There's no midterm, Amir. There's a final. Remember, there's a test for every chapter. No, you didn't see the updated. There's no midterm. Okay? All right, so everybody have a good weekend. Enjoy the weather. It's supposed to be good. And remember, well, Monday's a holiday, so there's no office hours, but if you do have questions, send them to me. Okay? Anyways, enjoy the weekend, everybody. Thank you.